Here we are on page 1 of the functions addendum. First we're going to talk about even and odd functions, which talks about the symmetry of functions. First we're going to start with our old friend, the quadratic or the parabola. Let's look at the parabola's values, and especially at x equals 3 and x equals negative 3. When you graph a parabola, remember that it looks kind of like this. And if you take the points x equals 3 and x equals negative 3, those correspond to the square of those values, and both of those values squared give the same result, which is y equals 9. Okay? So we see that at x equals 3 or x equals negative 3, we see that both values, or both y equals 9. And so we see that there's a symmetry about the y-axis, as if the y-axis was a mirror. Okay. So let's see the behavior when we substitute any value, then its opposite value, into the function f. Okay. So instead of substituting 3 and negative 3, we are going to put the values x and negative x. Although negative x, you might think, oh, that's a negative number. Negative x is not a negative number. Negative x is the opposite of whatever value you put into x. So if x happens to be a negative number, like negative 2, negative 2 is actually positive 2. So negative x doesn't mean a negative number. It means the opposite of the value you put into x. Okay? So we know that if you put x into the function x squared, you get x squared. But what do you get if you put in negative x into the function x squared? So we put negative x in for x, and we get negative x times negative x, which is equal to positive x squared. You see, you get the exact same thing out as when you substituted in regular x. Okay. Now we're getting to the definition of even function. A function f of x is even if the function when you put in the opposite of x is the same as the function when you put in x itself. Okay? So when you put in 3 and negative 3 into the function, you get the same value of y, is basically what they're saying. The graph of an even function is symmetrical about the y-axis. Okay. Consider the function f of x equals x cubed. What do you see when you compare the values of f of 2 and f of negative 2 by graphing or substitution? Okay, just to refresh your memory, x cubed looks like that. Okay, the negative values of x for x cubed become negative values of y. So if you put in f of 2, you get y equals 8. And if you put f of negative 2, then you see you get y equals negative 8. So they're kind of related, but they're not the same value, right? So f of 2 gives you 8. And f of negative 2 gives you negative 8. Okay. Let's see the behavior when we substitute any value and then its opposite value into the function f. Okay, so instead of just substituting real numbers like 2 and negative 2, we're going to substitute in values that represent any number, like x and negative x. So we're going to put negative x. We already know what happens if you put x cubed into f of x. You get x cubed. What happens if you put negative x into x cubed? So we'd have negative x cubed. That would be negative x times negative x times negative x, which would be equal to negative times negative times negative gives a negative. You would get negative x cubed. Okay. So a function f of x is odd if, when you put in the opposite of x into the function, you get negative of the value for the function you get when you put in x. So remember, if you put in x into x cubed, you just get x cubed. If you put in negative x into x cubed, you get the x cubed, but you have a negative outside of it. So do you see how this is an example of an odd function? Okay, so the graph of an odd function is symmetrical if you rotate the function. Okay. Okay, so let's see how that works. When you put in the negative values, you end up getting values that look like the right side, but they go down instead of up in this case, right? But what if you rotate the blue part? If you rotate the blue part, then you see that you're going to end up being on top of the red part, right? So by rotating the function, you can see that they are indeed symmetrical. Okay. All right, number 1. Show that f of x equals this function is an even function. Okay, so the way we're going to do that is remember that for an even function, we know that if we put the opposite of x in for the function, we will see that it is equal to the function, original function. Okay, so we're going to do that. We're going to take this, which is f of x, and we're going to see what f of negative x is, and we're going to show that they're the same. So what we're going to do is we're going to replace every instance of x, and we're going to put in parentheses negative x squared. And remember to put in the parentheses, especially inside of the squared, because if you put parentheses or don't put parentheses, it's going to make a difference. Negative x times negative x is actually x squared. And now you can see that, oh, I got the exact same thing as I started with, which is f of x. So I have shown that f of negative x is equal to f of x, so it is an even function. Okay? All right, number 3. Determine whether the following functions are even, odd, or neither. Okay. So, y equals 5x is a diagonal line with a slope of 5, quite steep. Okay. So, now, does this have any kind of symmetry? Well, it's obviously not an even function, because an even function has symmetry about the y-axis, and this does not, okay? So what about rotational symmetry? If I rotate it 180 degrees, is it symmetrical with itself? Yes, it is, right? I could rotate this 180 degrees, and it would be symmetrical with itself. So I would say that this is an odd function, okay? Next one. F of x equals 3 over x squared minus 4. What if we did the test for even functions? So we are going to put in negative x into here, and we'll get negative x squared minus 4, and that is equal to 3 over x squared minus 4, which is equal to this, so it is even. Okay. Last one. X squared plus 7 over x squared minus 3. Let's try to do the same thing. We're going to put in negative x in for x, and we'll get negative x squared plus 7 over negative x squared minus 3, and that is equal to x squared plus 7 over x squared minus 3. And hey, that looks exactly like the original function, so this is also even. There's another way you could do part A. Instead of graphing it and doing it geometrically. We could put in f of negative x in for x here. So we'll see what f of negative x is equal to. It would be 5 times negative x, which will be equal to negative 5x. And then we're going to compare that to negative f of x. Negative f of x is negative 5x, and we see that, oh, they are equal. So that is a check to see if they are an odd function, because if this f of negative x is equal to negative f of x, then it's an odd function, right? Okay, so that's another way of doing it without graphing. Number 5. Suppose that g of x equals x plus 1 times 1 over x plus b, where b is a constant. Find b given that g is an odd function. Okay, so we know that if g is an odd function, it obeys the rule f of negative x is equal to negative f of x, right? So let's see if that helps us here. Or, I'm sorry, it's g, not f. G, okay. Now, so let's take this original function, And then we are going to substitute in negative x to see what happens. So if we put in negative x, we'll put negative x always in parentheses, just to be careful. Okay, and so we got this, and say, okay, what does this turn into? This turns into negative x plus 1, negative 1 over x plus b. Okay, and remember that this is an odd function. So if this is an odd function, then it obeys this rule, and I could rewrite this with a negative in front, and that should be equal to this, okay? So it should be equal to negative x plus 1 times 1 over x plus b. Okay, now let's check to see if this is true. We're going to expand each side, and then we're going to check to see if the terms equal each other, and to see, how the b affects it too. So we are going to expand these with FOIL. So the left one becomes negative x times negative 1 over x. Negative x times negative 1 over x is equal to 1. Now I'll do the inside. So 1 times negative 1 over x is negative 1 over x. We'll do the outside, which is b times negative x, which is negative bx. 1 times b is b. And then the right side is, I'm going to put the negative out here for now. X times 1 over x is 1. We're going to do the inside, which is 1 times 1 over x, which is 1 over x. And we'll do the outside, which is bx. And then we'll do the last term, which is plus b. Okay. Now we're going to distribute the negative sign. So on the right side, we're going to have negative 1 over x, minus bx, minus b. Now we're going to compare the left side and the right side. We see a lot of common terms that we could subtract from both sides and get rid of, like negative 1 over x here, negative 1 over x here. Let's add 1 over x to both sides and get rid of that, okay? So get rid of that. Then you see that negative bx appears on both sides also. Let's get rid of that by adding bx to both sides. So then we're just left with 1 plus b equals negative 1 minus b. So let's, 1 plus b, we'll write that out, simplifying it. Negative 1 minus b, okay, and then let's group the terms. So we'll put the constants on the left and we'll put the b's on the right. And so we'll end up with negative 2b on the right, and then on the left side we will add 1 to both sides, we'll get 2. So b, it turns out, equals negative 1. In order to preserve this rule here, b would have to be negative 1 in this case, right? It's just like an algebra problem extending this rule's application. Okay? That's it for page 1.